Let's look at sample test number 3. First question, which will cause an electron to move in a larger circle? Increasing speed, increasing charge, magnetic field, impossible to tell. So we need the formula for a charge moving in perpendicular to an electric field. R equals mv over qb. And so we're looking at moving a larger circle means makes R bigger. And so what would make R bigger in these cases? Increasing speed, yes. Increasing charge, no, it's in the bottom. Increasing magnetic field, no, it's in the bottom. Yes, we can tell, so that's not right. So the answer is A. All right, number 2. Consider a current carrying ring with a dotted line axis so it can rotate around this, in and out of the top can come in or out of the paper, rotates in the paper like that. Constant field going up, pick 2 true statements. The torque would be 0. Well, no, we've got current going, so we got I cross B, so this one, this side the force is out of the paper, and on this side we got I cross B, the force is going down into the paper. So we've got force on both these two parts. On these sides we got the current and the field are parallel to each other here, so the force is going to be 0 here on these sides, but we've got force there, so the torque would not be 0. The top would turn up out of the page, yes. The top of the ring is here, it would come out of the page, the bottom would go down, yes. The top would turn down into the page, no. The force on the left side would be 0, yes. So we got B and D. Alright. 2 parallel conducting wires are carrying currents in the same direction into the page. We can see here. The currents are non-zero and equal. So we got some sort of I's into the page here. The point with the strongest magnetic field is A, B, or C. Alright, so point B, let's just study that first. Let's look at this wire. So if we thumb is the current going in, the field from, if we call this 1 and 2, the field from 1 is going down. The field from 2 is going up in the same spot. And if they're equal and they're not 0, and this is in the middle, then the field is actually, the total field is those two added together, so B total would be 0 here. This one, field is going, making clockwise circles, so the field from B2, or sorry, this is 2. B2 is down here, and same thing. B1 is small because it's far away, but B1 is also going down here. Over here, still clockwise, so I1 or B1, but it's further away than this one, and B2 is also going up. All right, but overall, this point is farther away from the 2 wires as this point is close to this wire. And so I would say C is going to have the strongest field. Okay, according to Lenz's law, the direction of induced current in a conductor will be that which tends to produce which of the following effects? Greatest voltage? Nope. So Lenz's law just tells us that the induced current, or the current from the induced voltage, is going to oppose make a field that opposes the one that started it. So, so it doesn't have to do with voltage or heat. Oppose the field that produces it, yes. Enhance, no. That would be kind of magic or something. All right, C. An airplane with a wingspan of 10 meters flies parallel to the Earth's surface at a point where the downward component of the Earth's magnetic field is that. If the speed is 250, what is the closest value potential between the wingtips? All right, so we've got a plane. It's got 10 meters. Distance here is like our L. This is a plane. And we've got the field is straight down. 0.4 10 to the negative 4 Tesla. And the velocity is perpendicular to that, going this way. 250 meters per second. All right, so we got V cross B, so the force is going to force the electron, or the positive current would be this way, and so the positive charge would go that way, so negative charge would go this way, so we're going to get a potential difference across there. Anyway, we want the formula E equals BLV. We got everything nice and perpendicular, so the equation works. So B is 0.4 10 to the negative 4, and L is 1 meter. This is Tesla. and the velocity is 250 meters per second. So let's do that, 0.4 -4 times 250. We get 0.010 volts, unless I did something wrong there. Oh, yes, this is 10 meters, so it should be 0.10. There we go, that's one of the choices. That looks a little better, so that's A. Alrighty. Inserting a ferromagnetic material inside a solenoid originally filled with air will have what effects? Assume constant current. So for a solenoid, we got B equals mu naught I N over L with just air, right? But with something with the magnetic material in it, then we change mu naught to be mu sub R mu naught. All right, so mu sub R, ferromagnetic material, mu sub R is greater than 1. And so it will make the field be, it says assuming constant current, so assuming everything else is constant, the way the thing is built is also assumed to be constant. And so it will increase the field. Inductance, L is, let me get the equation right. Mu naught N squared mu sub R mu naught N squared A over L. L is inductance here, L is length here. Let's make these little L's. And so again, the relative permeability is in here, so it would make it be a larger number, and so it will increase the inductance. And so we've got A and C. Alrighty. Which are needed for a charge to feel a magnetic field? The charge needs to be moving, yes. No, it doesn't need to be large. The field doesn't have to be changing, not all of them. So we would say A. Okay. And the last one there, the path of a charged particle moving perpendicular to a magnetic field will be A. We kind of already talked about it up there, but remember, if it's got a velocity like this and the field, say, is out of the page, we got B, V cross B, it would be down. Anyway, so the force is going to be tangent to the circle, and it's going to, anyway, we talked about that. We're going to make it be in a circle, so that's A. Okay. Number 9. Consider two parallel wires carrying unequal non-zero currents in the same direction. So we got two wires with current in them. They're not the same size, but they are going in the same direction. What will happen here? So if we call this 1 and 2, the field from 1 is going like this, so it's going down here. And then if we do I cross B, the force on this wire pushes in, and so they do the same thing to each other, so the other one will also be pushing in, so they are attracted to each other, A. All right. Which is true about inductors or inductance? They can store energy like a capacitor, yes. Inductance is in henries, yes. Changing flux for one coil, yes. We got E equals N d phi dt. They're on the same core, yes. Circuit symbol is like this, looks like a spring, yes. That's all of them, A, B, C, and D. Okay. Which is true about magnetic poles and electric charges? Electric dipoles can be separated, yes. Magnetic ones can't, that's true. Static charges feel electric fields, yes, but not magnetic fields, true. Likes attract, opposites repel, no, just the opposite of that. Electric forces are parallel to the fields, but magnetic forces are, yes. So we got A, B, and D. All right. If we can can see. Looks like we can see. An electron is fired at a speed of 10 to the 7th meters per second in the x direction into a constant B field, uniform external magnetic field directed into the page. What force, magnitude, and direction does it experience? So we got V going that way, cross B down into the page, and so the force is the thumb is going to be up for the right hand roll, but it says electron, so it's going to be down. Should I use my left hand? All right, so the force will be down or in the negative j hat direction. And then what is its magnitude? Well, we've got two equations for force for magnetic fields, either IL cross B or QV cross B. And since we've got a charge and a velocity, we're going to use this one, and we can simplify it to QVB sine theta. And again, in this case, the velocity is perpendicular to the field, which is down in the page, so this whole thing becomes a 1. Theta is 90 degrees, and so sine theta is 1. And so force is QVB. Q, it's an electron, so 1.602 10 to the negative 19. We'll not worry about the negative sign on the charge. We're going to take care of the direction from the diagram. So that's Q, V, 1 times 10 to the 7th meters per second, and B, 35 milli, 10 to the negative 3 Tesla. So we've got 1.602 negative 19 times 1 10 to the 7th times 35 10 to the negative 3. All right, so force, still tiny force, but it's still electron. So 56.1 times 10 to the negative 15 newtons. And we can say it's in the negative j hat direction, or see the figure kind of a thing. Okay, draw the path of the electron in the field. All right, so this first force kind of gives us an idea. It's moving this way, but it's feeling a push down, so it's going to go a little bit like this, it's going to go a little bit like this, it's going to keep turning, trying to make a circle here. So the path will be a circle in the field. It's a moving charge, moving perpendicular to the field. All right, what is the kinetic energy of the electron? Ke is 1/2 mv squared, 1/2 mass of an electron, 911 times 10 to the negative 31 kilograms. Velocity is 10 to the 7th meters per second. All right, so we got kinetic energy, plug that in. Half times m times v, which is 1e7 squared, 45.6 times 10 to the negative 18 joules. All right, let's keep 45.55 10 to the negative 18. Keep that for another calculation here that I happen to know that we're going to be doing here. So what potential difference would be needed to get the electron up to speed from rest? So this is thinking of now, first we're going to have some sort of a gun in here, parallel plates that are going to have a hole in it, just like we did before where we had charges here, and we're going to, probably drawing my pictures all wrong. But basically, we're going to have some sort of potential difference that we're going to fire the electron out, use to fire the electron out. So we've got kinetic energy 1 plus potential energy 1 equals kinetic energy 2 plus potential energy 2. And it says starting from rest, so kinetic energy 1 is 0, and then the ending is what we just got here, is this. All right, and so we can say potential energy to, let's just do PE2 minus PE1. PE2 minus PE1, bring this one to the other side, negative KE2. But this is delta PE, right? And we have from last time, delta PE is Q delta V, right? And so we're asked for what is delta V. And so we can say Q delta V equals negative KE2, or delta V equals negative KE2 over Q, which is negative 45.55, 10 to the negative 18 joules divided by Q of the electron, negative 1.602, 10 to negative 19 coulombs. Let me plug all that in. 45.55, negative 18 divided by 1.602, negative 19. .4 volts. Just double check my work here. I'll plug that in. 45.55 negative 18 divided by 1.602, negative 19. That's 283. I did something wrong with my calculator. 283 volts. It's a little high, but we'll go with it. That's delta V. All right. Potential difference, yes. Okay, moving on. So we've got some diagrams here that we're going to have to use our right-hand rule and figure things out. So let's see, draw and label the force on the wire. So we've got a wire current going into the page here. So we've got I going down in, cross B going that way. So the force must be this way. Alright, here's another one. Draw the velocity vector for a proton. So where's the force? So we've got the answer is F, and B is down. So we got I, or V cross B gives F. So the velocity must be straight up, or on the page up. Okay. Label the north and south magnetic poles on the solenoid. Well, it shows you the fields, so that makes it easy. Because the north pole, the field lines always come out of the north pole and go into the south pole. Alrighty. Direction the magnet is moving to cause this current. So the current is going around in the front of the loop like this, and so the loop is making a field on the inside. We're always worrying about the inside on these problems. So the loop is making a field coming around and going in. Right, so it's trying to increase the field inside, going that way. So it's opposing the field here. So that must mean this field is getting stronger in the kind of down left direction. Right, that's the direction it's pointing. These arrows are going this way. And so this field is trying to fight against a growing field in that direction. Right, so if it's growing in that direction, it means the magnet must be getting closer. Right, the magnet must be coming in closer because the field is stronger close to the magnet. Right, so if the magnet's coming in closer, the left pointing field is growing, and this is going to say no, go to the right instead. So I would say the velocity is this way, or up and right, I guess, is the direction the magnet is moving in towards the center of the circle. Okay, draw and describe the induced magnetic field near the conducting rod moving on the conducting rails. All right, so we've got an external field going down in, hopefully you can see that, and then the rail is coming this way, so the field is getting weaker inside there. There's getting to be less area, so there's getting to be less field, or less flux, right? It's always depending on the flux, d phi dt. So because the area is getting smaller, it's seeing less field, and so it's seeing less field going down, so it's going to want to make more field going down to keep the change from happening, right? So it wants to, doesn't like change, so it says keep my down field. And so on the inside, get my hand going, so the current needs to be going this way, right? So that inside the loop, the field is going down in, this would be the induced field, around, anyway, all the way around the whole thing. The current over here is going down this way, or going across this way, and again, it's trying to make a field down in, right? So it's going like this, or in on the outside, out on the, in on the inside, out on the outside, kind of thing. Different ways to draw the induced field, but all right, because induced fields fight the change. They're doing the opposite of what's causing it. All right, so we would say draw and describe the induced magnetic field. And so we would say down inside the wire, or down inside the loop, I guess. All right. F, draw the field experienced by the wire on the right due to the wire on the left. All right, so we want to know what is the field over here. So again, we got our right-hand rule. Thumb is the current. We're going around like this. Think of kind of grabbing hold of the wire, twisting your hand around. So over here, it's going down into the page, right? And so the B, all these are B from the right onto the left, right? Going down into the page. Draw the field experience. Yeah, so that's all it's asking for. Assume 3 conducting rings are moving to the right at 2 meters per second. Assume the magnetic field is constant uniform, has the boundaries shown, and is directed into the page. Draw the induced currents on each of the 3 rings. Okay, so this first ring is coming in, so it's feeling a growing field down. So it's going to say, no, I don't want it down, I want 0. It's coming from 0 field, so the field is growing down, so it's going to say, no, I want to go up. And then it's always talking about on the inside, so we want the field, the induced field from this guy to be coming up. And to make that happen, the current needs to be going around like this. And of course, it's the same current everywhere. It's all a closed loop, the same electrons going around in a circle, right? All right, something like that. So of course, coming up on the inside means it's going down on the outside. I don't know how we want to, if we want to draw everything, but okay. This one is in constant field and it's moving, so its area is not changing, the field's not changing, and so this one has 0 current, no induced current, no change. Got to have d phi dt to get a voltage, and you have to have voltage to get a current, so there's no voltage source, so there's no current. All right, finally this one, it has been in a strong field going down, and now it's losing that field, so it says, hey, I want my down field, so it's going to try to make a field down. So its current is going to go clockwise everywhere, right, same current, so that it can make a field in the center going down. So of course then on the outside it'll be going out, but just like this everywhere. Just drawing a few. This is B induced. B induced. Over here there's no induced, there's no current, so there's no induced fields. Draw the field caused by the induced current on the, yeah, okay, we already did that. Okay, next. Consider power line 7 meters above my garden. Assume the line carries 100 amps of current. Find the magnetic field. So we got power line, current, and one of the wires 100 amps. Got a garden down here. The distance 7 meters. All right, and so we've got, if we got a current like this, we got the field is going to be going down here. It's going to be straight into the page, right? Current going like that. So this would be the B field from the wire, from the power line. Okay, so the distance R is 7 meters. So we have B for a long wire is mu naught I over 2 pi R. So mu naught 4 pi to the negative 7. I is 100 amps. 2 pi R is 7 meters. 2 pi cancels with the 4 pi. We get a 2 left over. So we get 2 times 10 to the negative 7 times 100 divided by 7. 2.86 microteslas. All right, pretty small. Could ask, what is that in Gauss? When Gauss is 10 to the negative 4 Tesla, so it's multiply this number times, so we got Gauss. Let's just go ahead and write it out. 2.86 times 10 to the negative 6 Tesla, and we want Gauss, so we got 1 Gauss is 10 to the negative 4 Tesla. And so to get this number to be in Gauss, divide by 10 to the negative 4. Divided by 1e negative 4. And so we get 0.028 Gauss, which is 286, which is very small, all right? Because normal field for a garden is like 0.2 to the Earth's field on the surface of the Earth is like 0.2 to 0.6 Gauss. So very small for this setup that I've gotten here. Draw the sketch, include direction for the current and magnetic field of my garden. I already did that right there. All right, now consider 2 parallel lines centered above my garden, each with 100 amps, but going in opposite directions. Draw the field components and the total field. So now we're going to have like one power line here. I'm going to draw it at a different angle here, looking straight on the lines going into and out of the page. My garden down here. All right, and so I guess we can kind of just assume these are both still 7 meters, but it's going to make like a triangle, a little bit of a triangle here, some distance apart that wasn't given. All right, so the B field, let's go with this one first. So the B field from this one, current's coming straight out of the page, so the field is going to be perpendicular to it, to this radius. So the B field, we call this 1 and this 2, so B1. All right. Again, current's coming out of the page, and so it's going around like this, so we have B there. For this one, current's going into the page, and so we're going to curl like this. So again, it's got to be perpendicular to this radius now. So we're going to have B2, something like that. These should be the same size since they're the same size current. That's the same distance away, and so it's going to make some kind of a triangle here, and the x component here is going to be equal and opposite the x component here, and the y components are going to add on each other, so the total will be something like this going straight up. Unless you have your x and your two currents the opposite direction, they'll be going straight down, but it just depends on how you do your currents, but something along those lines. The sideways components will cancel, and the up and down components, up or down, will add up. Okay, so it says just draw them. It doesn't say we have to calculate them. If we did want to calculate them, we do B total is going to be B1 plus B2, and we would have to figure out the components, x and y components, and add them up as vectors. Okay. Moving on, number 16. Consider a wire wound onto a solenoid, radius 1 meter, length of 0.75 meters. That's a big one. If the solenoid has 500 loops, what current is needed to produce 10 millitesla field in the center of the solenoid? All right, so we've got kind of crazy numbers, but we'll go with it. B for a solenoid. B, mu naught Ni over length of the solenoid. All right, so 4 pi 10 to negative 7 times n, 500 loops. Times I. Excuse me. Times I. Oh, that's what we're looking for, is I. Divided by L, 0.75 meters. And we're given that this, we want, 10 milliteslas, 0.010 Tesla. All right, so maybe it would be better to rearrange this and solve for I in the first place. So I, just rearranging, multiply by L, divide through by the things multiplying I, so it's going to be BL over mu naught N. So it's going to be 0.01 times 0.75 Teslas meters divided by 4 pi 10 to negative 7. Very happy bird out there right now. 500 turns. Okay, let's do that. 0.01 times 0.75 divided by 500 times 4e negative 7 times pi. Okay. 11.9 amps, if I did that right. Just check my numbers. It's not what I got last time. But I think I made a mistake last time. Okay. Looks good. What is the inductance of the coil? Good question. All right, so let's find our inductance equation. L mu naught N squared A over L. L is the length of the coil of the solenoid. And so, let's see, A is the area here for the path. So area there. We need a radius. Yes. Okay, so R equals 0.1 meters, and so A is pi r squared, pi times 0.1 times 0.1 squared. We can just plug that in down here, I guess. So plugging everything in, mu naught, 4 pi 10 to negative 7, n 500, A pi times 0.1 squared, that's negative 7, and L is 0.75 meters. Little l. So let's see. So we've got pi times 4 10 to the negative 7 times 500 squared times another pi times 0.1 squared. All that divided by 0.75. 13.2 millihenries. Okay. Looks good. Again, we wouldn't tend to make, anyway, it's a huge thing, but we would tend to make inductors with iron cores, but this is just for an air core. Okay. And they would probably have more turns than that, but I think we did the math all right. Let's look at the next one here. Assume a metal bar on metal rails. L is, we got a number for L, we got a number for the width here. Or we should have a number for, or I guess it doesn't matter. Maybe it doesn't matter, or maybe I made a mistake. We'll see. All right. And assume a B field, we got that. Find the induced voltage in the loop made by the bar and rails if velocity is 10 meters per second. Alrighty. And so we can just go with our voltage E equals BLV. In this case, capital L is the length of the rail, which is what we're needing. And so we've got B, we got everything, I think. 5 times 10 to the negative 7 Teslas, and L is half a meter, and V is 10 meters per second. All right, so we got E, or we can call it V, the induced voltage. We call it give it a script E for EMF, but it's a voltage 5 times 10 to the negative 7 times 0.5 times 10. 2.5 times 10 to the negative 6 volts. 2.5 microvolts. Very tiny. Okay. Clearly label the direction of the induced current and the induced field on the diagram. Alright, so we're making a bigger area, so we're getting more field, more flux, and so more field going down, kind of idea, more field lines going down. So this is going to try to oppose that on the inside, so it's going to try to go up. So if we're doing this, I mean, on the inside of the loop, the current has to be going this way. Let's go the same way, kind of thing everywhere. All right, going like that, and so then the field is going, you can draw it like this, B field induced. It's going around, up on the inside, up on the inside of the loop every direction. All right, and coming down on the outside. Alrighty. What is the value, if R equals 0.25 ohms, what is the value of the current? Alright, well, we're just going to use Ver. Whoops. If I can write Ver. V equals IR. And so I equals V over R. The voltage is 2.5 microvolts. R is 0.25 ohms. So the current is 2.5 times 10 to the negative 6 divided by 0.25. 10 microamps. Yep. Okay. One more page. Consider an ideal transformer with 500 primary turns, so this is going to be N1, and 1400 secondary turns, that's going to be N2. Ideal voltage source connected to the primary, and resistive load is connected to the secondary. Draw the transformer with its coil, source, and load. So you could draw it as a 3D kind of a core if you want to. Two different sets here. One, the secondary has a resistor on it. The secondary is the 2 stuff, so it got a current and a voltage, and then the primary has a source on it. Got to be an AC source. We could draw the voltage V1 on the coil, or over here it's the same, they're in parallel. Or we could draw the more standard kind of circuit for a transformer. It's kind of like 2 inductors. And we have a resistor. We're going to have V1, V2, I1, I2. Generally we draw one current going in and one current going out. Makes the signs come out positive. Alright, so again, VS, V1 are the same thing. V2 is the voltage, V2 equals the voltage on the resistor. Okay, so draw, okay, we have drawn. If the primary current is 100 amps, whew, that's a big current, what will the secondary current be? Alright, so we've got 2 transformer equations, right? We've got I1 over I2, current goes opposite of the turns ratio, so that's N2 over N1, and we've got the voltage one that's going to be wanted down here, so we can write it V1 over V2 goes with N1 and N2. So those are the 2 main transformer equations. And so it says primary current is 100 amps, so primary is the 1 stuff, and so it's asking what is I2. So let's rewrite this with I2 on the top. I2 over I1 equals N1 over N2. Notice if 2 is on the top here for this side of with the currents, and the 1 is on the top on the ends. And so we can solve this for I2 is going to be N1 over N2, just multiply through by I1. So we've got all these numbers, 500 over 1400 times 100. So I2 is 500 over 14. 35.7 amps. Okay. What source voltage is needed to produce 120 volts on the secondary? So 120 volts on the secondary means V2 equals 120 volts. This is RMS, but we'll not worry about that right now. And so we're looking for source voltage, which means V1, which is Vs, is what? All right, so let's solve this for V1. V1 equals, crazy flies, V2 N1 over N2 equals 120 times N1 500 over N2 1400. All right, just plug that in. 120 times 500 divided by 1400. 42.9. Just double check that answer too, but I think that sounds about right. Somewhere. Yep, looks good. 42.9 volts is V1 is Vs. Okay, what is the resistance of the load? Okay, so we've got the resistance over here. The load is just the thing that's getting the current, the passive device on the end, and so we've got a VIR going on here. V equals IR. It's I2 and V2 that are associated with this. What is the resistance? Solve that for resistance. Just like we did in lab, we measured V over I. Got V2 over I2. V2 is the 120 volts, I2 is the 35.7 amps. It's like 3.36 ohms. Equals the resistance. Okay, looking good. One more problem. Again, this is an extra long test for sample problems and so forth. Yours will need to be shorter than this, but let's keep going. Consider two wires carrying the same current. So this is very much like we saw in the other picture, but we got some numbers here. So they're 30 centimeters apart, and B is at the center. So we got 15 here, and A is also 15 centimeters, so 0.15 meters. C is only 5 centimeters. This is in the center. Okay, we've got I1 is 5 amps going in. They're both going in. I2 is 7 amps going in. Okay, find the field strength from wire 1 at points A and B. Alrighty. So luckily points A and B are both 15 centimeters away, so it's going to be the same strength. B for a long wire, mu naught I over 2 pi r, so it's going to be 4 pi 10 to the negative 7 times I 5 amps, divided by 2 pi r is 0.15 meters. 2 pi's cancel with the 4 pi. This is a 2. It says negative 7. Okay, so we've got 2 10 to the negative 7 times 5 divided by 0.15. Okay, 6.67 times 10 to the negative 6 Tesla. B1 A and B. Okay, it's kind of hard to see here. All right, B1 at A and B, 6.67, 10, let's just say 6.67 microteslas. Okay, that's a little bit better. Find the field, draw the field from wire 1 at point B. Okay, so wire 1 is going in, so it's going to be going down, perpendicular. So, got stuff in the way. This is still 0.15 meters, but now B1 is like this. Something like that, going straight down. All right, find the field strength from wire 2 at point B. All right, so wire 2 going straight in, its field, it also is going clockwise. It's going to be going up like this. It's a little bit bigger current, so it's going to be a little bit bigger than B1, so this would be B2 vectors here. Should be going straight up because it's 90 degrees there. Find the field strength. Oh, let's find the field strength. All right, so same thing. B1 up here, B2, same long wire equation, mu naught I over 2 pi r, 4 pi 10 to the negative 7. This I, though, so this was I1, this is I2, this is 7 amps, and then 2 pi, and this R is the same R, 0.15 meter. It's the same distance, different. This R and this R are the same. Okay, plug those in. Let's cancel out. So we've got 2e negative 7 times 7 this time, divided by 0.15. 9.33 microteslas. Let me just check those numbers too. Maybe I don't have those before. Okay, hopefully I did those right. They seem fairly similar. Okay. Draw the field, I already did. Find the total field from both wires. So B total is going to be B1 plus B2. Luckily, they're both in the Y direction only. And so actually, we're adding them as vectors, but if we want to take up as positive, well, let's see. How should we explain this best? Well, so B1 is going down, right? So B1 has a negative J hat kind of a vector. And so this was just finding the strength, so that's just the magnitude. But if we're going to add them together, we got to take care of their signs. So B1 is going to be negative 6.67. We can call it J hat. And then B2 is going to be plus, because it's going up, 9.33 J hat. And these are all microteslas. Okay. Anyway, we've got to hopefully realize that they're going opposite directions. Since B2 is up, we'll take that as positive. So 9.33 minus 6.67, 2.66. So B total is 2.66 microteslas in the J hat positive direction, right? So B total as a vector. Okay. So it'll be just a little vector in here, B total, because it's the difference between those two. Oh, draw the total field. Yes, draw the total field. So B total is a little short one in here because it's up and then goes up from B2 but then down from B1. And so I didn't draw it to scale very well. Since B2 is 9 point something, this one is 2 or about 3. Anyway, something like that. I'll give the idea. Okay, I think that is the test.